This is a problem that is part of our 6.2 calorimetry section, and this is number 73 at the back of the book. This is a problem where you're going to solve for the heat capacity of a calorimeter, and then you're going to use that to further do the problem. So in this problem, we are using a bomb calorimeter, which means we're not using water, we're just burning something, and then the calorimeter itself will absorb that energy. So we're going to assume that the heat gained by the calorimeter equals the heat lost by, in this case, the combustion of methane. So what we're going to do is to calculate that amount of energy lost by the methane. We are going to take our mass of the methane, and we're going to want to convert it to mole. And then in the question, they're telling us that the enthalpy of combustion of methane is negative 802 kilojoules per mole. So really, methane plus oxygen, combustion, and then we would, in that process, release 802 kilojoules for every 1 mole of methane. So in our question, though, we don't have 1 mole, we have 6.79 grams. So I'm going to keep everything positive and think about my sign at the end. So in this case, I know that if I burn 6.79 grams of methane, I'm going to have 340 kilojoules of energy that is released. So based on that, now I'm ready to answer A. So A is the heat capacity of the calorimeter, which we use a capital C for. And this is equal to the amount of energy change that happens per degree Celsius. So in this problem, when we burned the methane, we had 340 kilojoules of energy that the calorimeter absorbed. We're assuming all of the energy from the combustion goes into the calorimeter. And in the question, we know that the temperature of the calorimeter changed by 10.8 degrees Celsius. So now I know I know the heat capacity of the calorimeter is 31.5 kilojoules per Celsius. So once I determine that heat capacity of that particular calorimeter, I can use that to figure out the energy of combustion of other things. So for letter B, we have 12.6 grams of acetylene, which is what they use in welding, and we know that it changes temperature by 16.9 degrees Celsius. So we're going to assume that the heat lost by the acetylene combustion equals the heat gained by the calorimeter. And we can calculate that by taking the temperature change times the heat capacity of that calorimeter. So we just calculated, I never did calculate, sorry, the answer to, it is right here. Sorry, here's the heat capacity of this particular calorimeter is 31.5. And then when we burned the acetylene, we got a temperature change of 16.9. So we can figure out how much energy was released by the combustion of the acetylene. So 532 kilojoules were released, but heat of combustion values are per gram or per mole. So this time we're going to give the value of delta H of combustion in kilojoule per mole. So in order to do that, we have to take the moles of our acetylene and convert that into, the grams of acetylene into moles. So 0.4843 moles of C2H2. So my delta H of combustion, I'm going to grab this, try to bring it down, is going to equal 532 kilojoules per 0.4843 moles, which would give me 747.4 kilojoule per mole. And then I, at the very end, want to think about it. This is combustion. This is exothermic. So my delta H of combustion is going to be negative 747 kilojoules per mole. So I'm not worrying about the sign until the very end. And I hope that helps. There's more problems like this in the back of the book.